There's an important distinction to make between cause and effect when analyzing the motion of objects. There are two very separate questions that we can ask. The first is, how does a particular object move? This is a purely descriptive, geometrical question that we're asking. What does the geometry of the motion look like? If we were to draw its trajectory as a function of time, what's the shape of that trajectory? The study of the geometry of motion of a trajectory is referred to as kinematics. The second question we can ask is, why does an object move the way it does? Why does the kinematic description of the trajectory look the way it does? This concerns what the causes are of the motion and of the changes in that motion. The study of the cause behind the changes of motion is called dynamics. Newton's second law of motion connects these two questions. When we write F equals ma, this is more than just a mathematical identity. Physically, we're connecting two very different questions. And we can symbolize that by dividing the equation into its two sides. The right-hand side, the ma side, is essentially asking the question of how. How does the object move? What does that motion look like? It's a description, a geometric description of the object's motion. The left-hand side of the equation, where the forces are, answers the question of why. Why does the object move the way it does? What causes the motion to change? These are very different conceptually, and the remarkable thing about Newton's second law, in fact, one of Newton's signature accomplishments,
we would now like to begin our analysis of motion, and we'll start with one-dimensional motion. Let's just consider a person running along a road. And so here's our runner, and here's our road. And what we want to do is be able to describe the position, the velocity, the acceleration of this runner. In order to do that, we need our first mathematical tool, which is a coordinate system. What is a coordinate system? Well, the first thing that we want to choose is an origin. We can pick the origin anywhere we want. That's a degree of freedom. So let's choose a point along our road as our origin. The next thing to do is to choose an axis. Well, the road is naturally defining an axis for our problem, and so we'll call this the x-axis. Now, along with that axis, we want to divide that up into some type of units. So we might divide our axis like this. And what's important here is to introduce a positive coordinate direction. And so the way I'll do that is I'll call this the plus x, and on this side of the origin, x is negative. Now, the third most important thing is that we're going to talk about vectors in physics. So we want a choice of unit vector. Now, because it's only one-dimensional motion, we only need one unit vector. So what that means is a choice of a unit vector at every point. Let's just consider a point here, P1. So our unit vector, I'll call it I hat 1. Now let's pick another point here. We'll call this the point P2. And over here, we'll choose a unit vector I hat 2. So every single point in space has a unit vector. Now what's unique about this one-dimensional linear Cartesian coordinate system is the following. These unit vectors have the same magnitude. A unit vector, by definition, has magnitude 1. And they're pointing in a positive direction because they have the same magnitude and direction. Next, begin to describe the position and the velocity of our object as it's moving along this x direction. Now that we've described the instantaneous velocity of an object, we'd now like to describe what its acceleration is. Velocity and acceleration are complicated things. One of the reasons why acceleration is such an abstract quantity is, for example, if I take this marker that's in my hand and I throw it up in the air and I catch it, you can see with your eye velocity. You can see the speed, you have a sense for it, you can see it change its direction. So velocity is something that, as a human being with our eye as a mechanism for determining motion, velocity is a very basic concept. But acceleration is a much harder concept. For instance, when I take that same object and I drop that, as it falls down, its velocity is increasing, and so we say it has an acceleration. But is that acceleration a function of time? Or is it constant in time? Is it varying in time? Is it a polynomial? Is it a constant? Those are much harder to see. Again, let's drop this object. So when I drop that object and I catch it down here, our eye does not tell us intuitively anything about the mathematical nature of that acceleration. And that's why acceleration is a much more abstract quantity. In fact, a great question is the following. When I throw this object up in the air, let's focus at its highest point. So I throw it in the air, and it comes down. When the object was at its highest point, was its velocity 0? Was it its acceleration 0 or non-zero? A hint to this question is in Newton's second law, F equals ma. If there's a force acting on this object, there must be an acceleration, and that force is the gravitational force. And when this object was at the top of its motion, I didn't turn the Earth off. So there's still a gravitational force. And so for an object in free fall, now free fall just is which means under the influence of the gravitational force we can conclude from Newton's second law that the gravitational force, ma, so this gravitational force is non-zero, and so therefore the acceleration is also non-zero. So once again, as I throw this object up in the air, nobody turned gravity off, we're not in empty space, and near the surface of the Earth, the gravitational force is not zero, the acceleration is not zero, so throughout this motion, this object is accelerating. I choose a example to show you that acceleration is a very abstract concept, and now our goal is to figure out how to mathematically define acceleration in terms of our velocity. Let's consider a two-dimensional motion. Suppose we have something like a projectile motion, and we have an object moving. Let's now describe how we can describe this motion with vectors. So the first thing we always want to do, and let's remind ourselves of the steps, is we want to choose a coordinate system. Now, what does a coordinate system consist of? It consists of an origin. It consists of two axes. In this case, we'll identify the positive direction for each axis as plus x and plus y. And at every single point in space, so if we had any arbitrary point P, here, P, let's call this P1, we have a choice of unit vectors I hat 1 and j hat 1. Now, what makes Cartesian coordinates unique is that no matter what point we're at, the unit vectors are all the same. So we could erase all these indices for that particular point and just have an abstract set of unit vectors I hat and j hat. Now, normally what we'll do is we'll just put those off to the side. So in our Cartesian coordinates, we now want to define the position vector. And the position vector is a vector from the origin to where the object is. So we'll write that position vector. We'll denote it by r of t, because as this object moves along its trajectory, that position vector is changing. And we'll write down r of t in terms of two coordinate functions. x of t and y of t. And so our vector, position vector of the object, r of t, is equal to x of t I hat plus y of t j hat. And one of our main goals is to figure out what these position functions are for the motion of objects. So this is how we describe an object in a Cartesian coordinate system undergoing two-dimensional motion. What we want to analyze next is what is the velocity of that object.
I'd like to talk to you about solving these kinematics problems. So we're going to actually start by asking ourselves 3 separate questions anytime we start one of these kinematics problems, and this will help us really figure out what's happening in the motion. So the first question that we want to ask is how many objects are moving? So do we care about more than one object? And if we do, we need to make sure to label each one distinctively. We also want to know how many dimensions we need to care about for each object. The second question that we want to ask ourselves is how many stages of motion does each object have? So for example, if you're told that a bicycle is initially accelerating and then at a certain time it stops accelerating, then you know that initial acceleration is going to have different equations of motion than the point in time where it now has an acceleration equal to 0. The final thing that we want to think about, we want to figure out what special conditions there are. So, for example, you might be told that the cart is initially at rest. So what does that mean in reality? It means that you can write down something like v of 0 is equal to 0. That's what it means for the cart to initially be at rest. The cart is v at time 0 is equal to 0. So those are the kinds of special conditions that you need to pay attention for in the problem, and that will help you figure out, get all of the numbers or the variables that you need to solve your equation. Once you're done thinking through these different steps, the final thing you should always do before starting a problem is draw out your problem, properly label your system, and then, of course, draw your origin, your axes, and your unit vectors. And this way, it'll be easy for you to organize all of the different information that you have.